Welcome students. So we'll discuss now the system of first order linear differential equations. Note that we spent three classes, prior classes, trying to build up the setup on how to attack this theory or these kind of problems. So recall, what is a system of first order linear differential equations? It is a form x1 prime is p11 x1 plus dot p1 xn plus g1, and same way all the way until xn prime is pn1 x1 pnn xn plus gn. So here note that your x are functions of t, your pij's are also functions of t. So for all I and j between 1 to n, and not only that, gi's are all functions of t. So now we will write this system in the matrix form. So for that, let's call this vector x of t will be x1, x2. So these are all functions of t. So even if I do not write t, it's clear that they are functions of t. Let's call g vector g of t to be g1, and matrix P of t to be P11T, P1T, P1N, P2N. So this is your matrix P, and you can write it in a slightly more compact form as x prime t, because you see there are derivatives involved here. So x prime of t is p t of x plus g of t. So the above system of homogeneous first order linear differential equations can be written in compact form in the following way. Yeah, in the following form here. Okay. Now note that this system is called homogeneous if g of t is what? 0. So here g is written in bold. So if you want to write it, I'm putting an arrow on top of it to indicate that it's an arrow. Okay. So in that case, you'll be given as pt of x. So note that these two are matrices. So these two are vectors. And this is a matrix. This is an n by n matrix. Whereas these are n cross 1 vectors, or you can call them column vectors. Okay. So now we want to understand. So again, our goal, as always, is to understand the system or given differential equation or system of differential equations. So we want to understand the system of first order linear differential equations. Namely, we want to understand their solutions. Okay? So the superimposition principle applies here as well. So what is the superimposition principle? So recall, suppose K are solutions to the homogeneous problem x prime equals to p t of x. Then recall the superposition principle tells you that if you take linear combination of these solutions, you still get a solution. Then any linear combination so where you have C1 x1, C2 x2, CK xk is also a solution. For C1, CK belonging to R fixed. Okay. So let's call this as X and see that this indeed satisfies the differential equation given that x1, x2, xn, xk, satisfy this homogeneous problem. So the proof is by direct calculation. So we have bar, take this guy and differentiate this. That would be same as basically d by dx, or d by what? dt of x, not d by dx because the variable is t of this guy, which is going to be d by dt. So if you recall so I'll stop writing t, but it's understood that they are functions of t. There's no ambiguity in that. And now using the linearity about the derivatives we saw in the last one, we see that this is going to be C1 prime plus C2 CK. But note that these x1, x2, xk satisfy this differential system of differential equation. What does it mean? It means that x prime equals to p of t. Yeah, this is exactly what it means. So I'm going to replace this now by C1 p of t of x1 ck p of t. Okay, now I'll basically take so CIs are constant, so they can commute with the matrix and they will go inside. So I can take P of T common, and what is left in the bracket, C1 CK. Now this is exactly what your X is. So that you get P T of X. Yeah. So therefore, what is the upshot of this? Therefore, any linear combination is also a solution. All right. So this is proved. Good, or at demonstratum. Now we want to talk about a general solution of a homogeneous system. So suppose we have a vector function x1, x2, xn are the solutions to the system of differential equation x prime equals to p of tx on any interval I and are linearly independent vector functions, then any solution of x prime equals to p of t of x can be written as a linear combination of these guys. So let's again try to understand what is the starting setup. So p of t, so P of T is an n cross n matrix. Yeah? The dimensions have to match properly, right? So P of T is an n cross n, and we have what? P of T is an n cross n, and these are n cross 1 vectors. Okay. So then it says that if you take these solutions and they are linearly independent on interval I, then any solution can be written as a linear combination of this in exactly one way. Okay. So in this case, we call x of t is called general solution, and these guys form a fundamental set of solution. Is a fundamental set of solution. Yeah, note the word right? I mean, like, so. So now we want to, okay, so given n solutions, you want to check whether they are linearly independent or not. Yeah, why? Because we want to, because if they are linearly independent, then we get the fundamental set of solution. So like in the previous setup, we want to find out the fundamental set of solution. So in general, it may be hard to check if the given vector functions are linearly independent or not. Hard is not the right word, it is tedious. So how do we basically bypass that? So the idea behind that is the idea of Wronskian. So again, let x of t dot 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 be solution to equals to p of t x. Now form a matrix by concatenating them as as columns. So you get matrix x, x1, x2, xn. Now note that this matrix will be an n cross n matrix, all right? That is important. Otherwise, you can't define few things, right? Say, for example, then we define Wronskian of these solutions to be determinant of x of t. Now note that, again, I'll point this out here, that the dimension should be right so that we get a square matrix, all right? So if you're looking at n cross n matrix or n system of equations with n variables, you are looking at n solutions, all right? And then you're determining whether you're determining or finding the Wronskian. Otherwise, the definition of Wronskian won't make sense. So now, how do we find out this Wronskian? Okay, so we have to compute this determinant. Now, there is a variation of Abel's theorem as well here. So Abel's theorem says the following. So suppose x1 dot 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 xn are solutions to the dE, x prime equals to p of px. Again, xi's are n cross 1 vectors. Vector functions to be precise, or n cross 1 vector functions. All right, so we have the following setup. Then the Wronskian, and then on interval I, so they are solutions on interval I, and then on this interval, the Wronskian is identically 0 or it never vanishes. So basically tells you that either Wronskian is non-zero completely or it never vanishes. So this gives you a way to compute the, so Abel's theorem tells you that if you look at the Wronskian, then you will have the Wronskian satisfies P11T, all the diagonal terms, T, P, N, T. Okay. So this is what the Wronskian of the fundamental set of solution will satisfy. Okay. So this means the Wronskian can be computed as C times exponentiation of integral P11T plus P22T dot dot PNNT dt, and then exponentiation bracket close. So let me just put the bracket with a different color so it's clear what is happening. And this is called Abel's formula. Okay. So now let's look at an example. So let your differential equation be given by 2 minus 1, 3 minus 2 x. So your solutions are also given to you. Solutions are given x1 of t is 1, 1, e to the t, x2, 1, 3, e to the minus t. So these are the set of solutions. So now, first, verify that these are solutions. Or solutions. So how do you verify? So what is their left-hand side? So left-hand side, basically, so verify means it should satisfy this star. So let me check it for x1. So you can see what is x1 prime will be taking the derivative of this guy, which will be the same, right? 1, 1 e to the power t, because exponential derivative does not changes. So what about RHS? The right hand side would be 2 minus 1, 3 minus 2 multiplied by 1, 1 e to the t. E to the t is a constant, so I can, e to the t is a scalar, right? It's not a constant, it's a scalar, so it is out. So let's keep it out. Multiply it, so 2 times minus 1 is minus 1, 3, so you get 1 e to the power t. So LHS equals to RHS. Therefore, x1 is indeed a solution to the system of differential equation labeled by star. Okay. Similarly, we can check that x2 is also a solution. Okay, so that I'll leave it to you for checking. So two. Now we can check that x equals to c1 x1 plus c2 is also a solution. Yeah, this is verified by our theorem above, but you can check to check it. Now, third, we want to show that these solutions form a fundamental set. Okay, so now to show that, we need to show that they are, so one, they are linearly independent. So how do I show that they are linearly independent? So let's take A times 1 plus B times, or let's say C1 times zero for all t. Then show that C1 equals to C2 equals to 0 is the only possibility. Right? Now 4, so problem 4, find a solution that satisfies the initial condition of 0 equals to 1, 2 transpose. Now this is not hard to do. Let's just do this problem. So we have x of t. The general solution is written as a linear combination of the two solutions. So let's see, what is x of 0 is going to be c1 times, let's see, so c1 is, so these are your solutions, right? So we get, so the solutions are, one is x1 is here and x2 is here. So let me write that down. So this equals to 0 would imply c1 times 1 1 because e to the power 0, okay, plus c2 times 1 3 e to the power 0. Okay, so this is minus t here, minus t, right? So you want to solve for it, so you get this equals to, what do we get? We get 1 comma 2. So now this will give us c1 plus c2 equals to 1, c1 plus 3 c2 equals to 2. Subtract them, you will get 2c2 equals to 1. So c2 is half. This implies c1 is half. So therefore, the solution is satisfying this initial condition. Your x of t is c1 which is half times 1, 1 e to the t plus half times 1, 3 e to the power minus t. So this is your solution satisfying the initial condition, right? Satisfying the initial condition. Okay. Now, so let's compute the Wronskian. So what is the Wronskian of these two solutions? So Wronskian of x1, x2 is going to be determinant of, so now I need to multiply this inside, right? So e to the t, e to the t. So it's basically, so I can write 1, 1 e to the t as e to the t, e to the t. The second one would be e to the power minus t, 3 e to the power minus t, right? So this is what the Wronskian is, all right? The Wronskian definition is different here compared to the second order differential equations, right? So this is going to be 3 minus what? 3 minus 1, which is 2. So this is the Wronskian. Now 6, show that Wronskian from 5 is a solution to Abel's equation What is Abel's equation? W prime equals to P11 plus P22 of W. So let's see. So does it satisfy it? So this is a Wronskian we got. So W prime is clearly 0. So left hand side is 0, right? Because we are using this value as your Wronskian, right? And what about RHS? So RHS is P11 plus P22. What is P11? So P11 is 2 and P22 is also minus 2. So P11 plus P22 is 0. So therefore this times W is equal to 0 times W. So therefore LHS equals to RHS. So the Abel's theorem is also verified. So what comes next? So that's about for this part. Next, we'll try to see how to find out these solutions, this fundamental set of solutions, right? Because here we were given these solutions, right? We are given these solutions, but how did they come to existence? We haven't dealt with that yet, and that would be the part of the next lecture. Thank you for your attention.